You are listening to the Wi-Fi Ninjas podcast, where we talk about wireless technology. Here are your hosts, Mac Daring and Matt Starling.
Hey everyone, Matt and Mac here. Welcome to the Wi-Fi Ninjas podcast. And today, again, it is just Matt and Mac. 2 weeks in a row. Well, not 2 weeks, but 2 episodes in a row, Mac.
That's
just us.
Unbelievable, isn't it? It's like we don't do it for a year, then we do it twice in a row.
I know.
Maybe people, they don't want to talk to us anymore.
Maybe. But I quite enjoy it when it's just us two as well.
Yeah, absolutely. We can level up a little bit and have like a studio in the middle, in between Boughton and Watford. Is it Watford? Bushy?
Yeah, just next to Watford in a place called Bushy.
Yeah, recording in person is even nicer.
Yeah, true. That's been a very long time. So what are we going to be talking about today, Mac?
Today we are talking about the game. So pretty much the topic that, I don't think it's covered well enough around their internet. It's like about how the devices, they access Wi-Fi medium, how does it work, what do they have to go through before they are even allowed to talk, and what happens if more than one device talks and this kind of stuff. It's a very important topic in Wi-Fi, one of the most important topic. If you understand that, you can say that you understand like how Wi-Fi works high level.
Sounds very interesting.
Yeah, so interesting that I'm about to cry again.
Well, I hope you've got plenty of tissues there. So the goal, Mac, in Wi-Fi, when we are going to be sending a transmission, right, is that we want to avoid collisions in Wi-Fi. We don't want to crash into other people's transmissions, do we? So is there ever a situation, where there are no collisions in Wi-Fi?
If you are the only person trying to talk with one device, then
what
probably...
do you mean?
Yes.
You trying to talk like right now?
Yes.
Is this collisions?
Two people.
Oh,
See, that's all it takes to have a collision. So if you have multiple devices, you will have collisions. The more devices you have in Wi-Fi, the more collisions you will have. The percentage of all the transmissions being a collisions, like ending up with a collision, will increase with the increase of the devices.
Exactly.
So high level.
So Wi-Fi is, see, look, we're having our collisions again, right? So Wi-Fi is very much like having a conversation. When two people trying to talk and communicate, just like how me and Mac are right now, one person's talking and the other person's listening. If you guys obviously listen to the podcast and then me and Mac were both trying to talk over each other, you probably couldn't even really understand what we were both trying to say. So you could hear us both talking, but you couldn't clearly make out what we were trying to say. That's like
listening to my dodgy accent, you can't understand me anyway without collisions.
Yeah, so you're like an 802.11b client, like legacy rubbish Wi-Fi client.
1997.
And I'm like 11ax, super efficient.
Yeah, on 6 gigahertz band.
No, that's Wi-Fi 6E, Mac. Come on.
How do you call it? AXE?
AXE, I don't know. It's so many different terms that you got to keep up with now, right?
Yeah. Okay. So very high level in Wi-Fi, our goal is to avoid collisions. When you have a wire connected to like a hub that you don't use today, and you have multiple devices in a single collision domains, and some devices, they will talk at the same time, the collision will be detected very quickly because you have different pairs of wire inside the cable used for transmission and used for receiving data, and they do it at the same time. So if collision occurs, then there is like a boom in the cable. You have everyone hears it and they back off momentarily. In Wi-Fi, it's not how it works. In Wi-Fi, when you talk and someone else talks at the same time, the receiving end will not understand the transmission, okay? And therefore, it will not send an acknowledgement. Every unicast frame in Wi-Fi is acknowledged. And if you don't have the acknowledgement, it means that the receiving end didn't receive the frame that you wanted to send, or it did receive it, it sent an acknowledgement, and you didn't receive the acknowledgement. Maybe there was a collision with the acknowledgement being sent back to you. So if you have a collision, you will have to retransmit. And retransmission, it takes time and resources. And if you have another collision, then you will have to retransmit again and again and again. So if you have multiple clients colliding frequently, then you will be retransmitting frequently. And it will take more airtime utilization, and you will be able to put less data in the air. And not only that, your latency will suck as well. So if you're on a voice conversation, you won't be able to maintain it. If you have high channel utilization, like layer 2 channel utilization, because of the devices colliding and sitting on backup timers as a punishment for the collisions. So that's high level thing. The goal is for one device to talk at any given time. So in cabled world, we are using CSMA CD. CD, it stands for collision detection. CSMA is carrier sense, multiple access, and CD, collision detection. In Wi-Fi, it's CSMA, so carrier sense, multiple access, but it's collision avoidance, CA at the end. CSMA, CA. We want to avoid collisions. If we don't, we have retransmission.
Exactly.
Thank you.
And let's say, we've got like one access point serving 10 clients. How does the access point and how do all of the Wi-Fi clients know when you're going to be transmitting, or like when it's going to be their turn? Like, how does that work? What do they see? What do they do? What happens? So there's an important field, right?
There is quite an important field. So in 8.11 header, we have a very important part of that header, that is the MAC header. And inside MAC header, we have all the MAC addresses, we have the frame control, and we have something that is called the duration ID. And duration ID is very important because when one device talks, sends data, when it starts its transmission, in its header, it will include the duration ID. And duration ID is the number of milliseconds, microseconds, that is required for the frame to be transmitted for the IFS timers that we're going to talk about in a sec, to allow some time for the receiving end to process that data, to send an acknowledgement, and for the transmitting end to get the acknowledgement, process it, and consider the transaction complete. That's the duration ID. Duration ID is the time where all the other devices participating in the Wi-Fi network exchange, is that the name?
Yeah.
They will have to wait for the game for the duration of the duration ID of a client that is currently transmitting.
So great analogy here is, let's say you join a video conferencing call and there's going to be 10 of you on that Zoom conferencing call. Imagine the duration ID is basically like you going onto that Zoom conferencing call and you announcing to everyone saying, hey, I've got this part of the conversation, I'm going to be talking now, that my part of this conversation for the next 2 minutes. Everyone now knows on the Zoom session that they are basically going to go on pause or not talk or try and talk for the next 2 minutes because they know you are going to be talking for the next 2 minutes. So they're not even going to bother trying to talk. That's why the duration ID is super important.
Yeah, or if you're a teacher and you're asking your class, guys, I will take questions at the end of this section. If you are respecting that teacher, it's not always the case, then you will hopefully end until the end of the section. In the meantime, you will be noting down your questions. And then when it's your turn to ask questions, you will do it. And you were idle for the duration ID time in microseconds.
Mm-hmm.
So that's a very quick recap into 8.11 header that contains duration ID that tells other clients not to transmit anything for the duration of the transmission.
One other good thing to just cover here as well, and since we were talking about the MAC header and the different type of addresses and the difference between CSMA CD and CSMA collision avoidance. So on the wire, how many address fields will we see compared to in wireless?
I don't know. Joking. So in the wire you have two, yeah, right? Just the source and destination. In Wi-Fi you have up to 4 MAC addresses, typically 3. Why do you ask?
I just think it's something that maybe not everyone is aware of, and there's another difference here, and it's good to know. So in wired, like you said, we have a source MAC address, destination MAC address. In Wi-Fi, we also have source and destination, but there's 2 additional addresses that we could potentially have: transmit and receive. So typically, like you said, most of the time it's going to be 3 addresses, but it can be up to 4.
Yeah, that is true. So let's assume that we have multiple devices that went through the full association process to the BSS ID of their choice. I think we have covered the green diamond stuff in one of our previous podcasts. Yep. Where we were talking about the decision making of a device before it decides which access point to join. Actually, it was the last podcast, I think, when we were discussing the roaming. So the devices, they have discovered all the access points, they have associated to or roamed to the BSSID of their choice. They are happily active clients in the Wi-Fi network, and they are all playing the game. They are contending for the airtime. So the more devices on a single channel you have, the more contention on that channel you will have when it comes to accessing the finite Wi-Fi medium, the air, to be able to put the electromagnetic energy when it's your turn in the air, so it's being received by the receiving end, and the receiving end can understand it. So let's assume that we have all these devices, and my device has won the game. We will spend more time talking about how the game looks like, but let's say that it's my turn to talk. I hope that no one else is going to talk at the same time as me. It is my turn to talk. The first thing that my device will do when it's its turn to talk, it will wait. So the active transmission starts with waiting. First, we wait DIFS. It's the interframe space timer that is 34 microseconds in OFDM transmissions. And after waiting for that timer to make sure that the medium is, clear, that no one is transmitting, I've waited this timer, then my device will transmit its data frame. You will have the duration ID put in there, like everything is in there. And then after sending the data frame, the device will wait for another time, SIFS, short interframe space, which is 16 microseconds this time. So I've waited diffs, I've sent data, now I'm waiting CIFS, and CIFS, it gives me the extra time to wait for the acknowledgement from the receiving end. Hopefully, if I was the only device transmitting at the same time on the same channel, the receiving end will understand my transmission, will process it, and it will send me an acknowledgement saying, Mac, thank you for your transmission, I received that. That's it. When I get the acknowledgement, then the transaction is over. And then the game continues. The duration ID that my device put in its MAC header comes to an end, and all the other devices, they resume playing the game. I say resume because when they are sitting on the duration ID timer, let's say for now, they are idle. They stop the game. They are not participating in the game anymore. Then the duration ID, it goes to 0, and then they will continue playing the game.
It goes to 0, but what do you mean it goes to 0? I think you're kind of touching on the contention window there, which we haven't discussed just yet.
Yeah, both, actually, because duration ID is like, that they will be counting down the microseconds in the duration ID. So when that reaches 0, then they will continue playing the game, at which point they will be counting down to 0 from their contention window timer, right?
Yeah, exactly. So the contention window is basically one of the processes that your Wi-Fi client device is going to do is going to pull a random number, and this random number refers to a slot time. So by default, the contention window, the first initial attempt is that your device will pull a random number between 0 to 15. And then the 15 isn't a time, it's more of it's pulling a slot time. It's pulling a number to count down in slot time, which is equivalent, changes based on the standard of Wi-Fi that you're using. So let's say the first initial attempt, you pull 6, you're counting down 6 slot times, but each slot time is a reference to a time based on the standard Wi-Fi that you're using. So in 11AC, I believe it's around 9 microseconds per slot time. So your device will pull that random number, start counting down its slot times. Hopefully when it gets to 0, if the medium is free, we will win the game and transmit our data.
And that's another thing to discuss in a sec. So the first thing that devices, all of them, when they wake up, when they finish their power save mode, when they have finished their association process and they want to transmit something, first thing they do is they will get the contention window number from the pools that Matt has explained, with first attempt being between 0 and 15. And why do we see first attempt? So that's another very important concept here, because you can have multiple attempts to send the same frame. Matt, why my device would not be able to send a frame, or would have to do it again? In what circumstances?
So if your device does not get an acknowledgement, then it will assume that the frame did not get there, because how does the device know? It can't see, it can only listen. So once you send your unicast frame in Wi-Fi, we need to receive that acknowledgement so we understand that it's got there. If it didn't get there for maybe there was a collision over the air, or maybe there's interference and the receiver wasn't able to receive your transmission, it can't give you that acknowledgement. You go, okay, fine, fair enough. You didn't receive my data frame. I'm going to try and send that to you again. But what happens now is that your contention window gets doubled. So you get punished each time that you have to send a retry in Wi-Fi. The random number that you pull from is doubled. So the starting one is between 0 to 15. No acknowledgement for your unicast frame. It then doubles to your first retry will be between 0 to 31. Now, this isn't to say that you might not pull a number lower than 15 in your first retry. You could pull a 3, and then, that's in that first initial attempt window. It's just statistically, you're more likely to pull a higher number. If you send your frame again on your first retry, there's a collision, there's interference, and the receiver's not able to acknowledge your frame, you go, okay, fine, fair enough, I'm going to try again. So your second retry, it gets doubled between 0 to 63. So each time you send your frame no acknowledgement and you retry, you get punished by doubling your contention window. All the way up to when you get up to your 6th retry, and the number that you'll be pulling from are between 0 to 1023. After that, all subsequent retries remain between 0 to 1023.
Yeah, and that's quite crazy in Wi-Fi terms, because we are talking about every single frame. Every single frame has to play the game, and if you have a lot of retransmissions, like the 6th retry, which is not unheard of, right? It's more than 1,000 microseconds, which is a millisecond. So if it happens a few times, you have to wait for 1 millisecond before your next attempt of putting a frame in the air. But this is just the contention window timer. Then you have the DIFS, then data frame transmission, then SIFS, then waiting for acknowledgement. Then you don't get the acknowledgement. So you wait again, your contention window timer, and we are starting to look at milliseconds of delay or tens of milliseconds. So when you are getting a delay, a latency of 150 milliseconds plus, then your voice transmission starts to sound weird. It's difficult for you to talk with someone on the other end. Mm-hmm. So you don't want to have that many retries and sitting being punished in a contention window timer. That is exactly why when you are in a busy network, in a busy Wi-Fi network, and you want to assess the quality of a network with something that doesn't make too much sense in Wi-Fi, like a ping test, you will see results like when you're pinging your, let's say, local gateway even, but you have a lot of contention in your network, tons of CCI, channel overlapping. So all the devices associated on a single channel, when they can hear each other, they will be contending for the same airtime, where only one device, ideally, will want to talk at the same time. So sometimes you will have ICMP packet coming back to you with a latency of 5 milliseconds. Sometimes it will be 500 milliseconds. Then it will be timeout, and then you'll on 10 milliseconds and 5 milliseconds again. And it's perfectly normal in a busy Wi-Fi environment.
Yeah, so Matt,
so that's the window.
Question. Let's say I come over to your house and we're sitting in your office, and I've got my iPhone, you've got your iPhone, and we're connected to the lovely access point that is just outside of your office. We're going to go through that process where my device is going to pull a random number, your device is going to pull a random number. Is there any way that my device knows or understands what the random number for the contention window that you've pulled is?
No. So the devices, they are getting the numbers from the same pseudo-random pools. So there's initial attempt between 0 and 15. It's a high chance of few percent that just with two devices, they will get the same contention window number. And if they do, what's going to happen?
There's the very strong likely potential that there's going to be a collision, which therefore will create a a need to have a retransmission, so your contention window then gets doubled, and it takes longer for us to access the medium. One thing that we could probably touch on here that kind of makes sense probably to bring it up now is QoS or 802.11e or WMM in Wi-Fi. What is that? How does it work? And what does that really do? Like, does it, if you're in the Cisco world and you apply the platinum QoS policy to your SSID, or if you are on using another vendor to apply QoS values, and you can set like voice, video, best effort, background, or platinum, gold, bronze, or silver. What does that actually do?
Yeah, so that's a very good question. So we are just talking about the QoS in the air. Mm-hmm. So it's only about the transmission between the station and the access point, or the other way around. So in the Wi-Fi QoS, you are just changing the duration of the initial timer from a diffs that was like a static 34 microseconds. I don't have it in front of me, so it's just from the top of my head now, all the timers. But the diffs without QoS in Wi-Fi, that is, QoS in Wi-Fi is called WMM, Wi-Fi Multimedia. It's a subset of a standard from ETCA, from IEEE. And within the subset, they describe 4 different classes. You have the background, best effort, video, and voice queue. And each of these queues or classes will have a different IFS timer at the beginning of the transmission. So when it was 34 microseconds without WMM QoS, now it will be a little bit longer for the background traffic. It will be around the same for the best effort traffic. And these timers will be shorter. The first IFS timers will be shorter for video transmissions and even shorter for the voice transmissions. By having this initial timer being shorter for every class that is more important, like voice is more important than the background traffic, for example, even if 2 devices, they draw the same contention window number, let's say they both have 5, and then after 5 slot times of 9 microseconds slot time in OFDM transmissions, after 5 slot times, they will try to send data at the same time, then the voice client will send data first because they reached 0 from the contention window timer perspective first, but then the initial timer was shorter, so the voice will start transmitting, and then the background traffic device that is about to transmit, when it sits on the IFS initial timer, it constantly checks if the medium is free or not, and it will see that there is something. It will be our voice client transmitting, and then it will just back off. It will take a look at the duration ID. It will update its nav timer that we are about to talk in a sec, and it will back off. It will pause the game. It will not transmit data. So that's how the timer is changed, the IFS initial timer. Another change is that the pools that these devices they are drawing contention windows from, they are also different. So let's say voice initial pool will be between 0 and 3, if I remember correctly.
Wow,
for video, it will be between 0 and 7.
Yeah, that sounds great, right? If you've got voice QoS set to on your corporate SSID, and now your Wi-Fi clients on that SSID, they only have to pull a number between 0 to 3, or pull a slot time between 0 and 3. That sounds fantastic. But what if you've got 30 clients all connected to that one access point on that SSID, where the initial attempt is now only pulling a random number between 0 and 3? Is that not more statistically likely that you're going to have a retransmission?
Of course it is. So if you have too many voice clients, then you will have tons of collisions as well. So we have to be careful with our design, making sure that we have enough capacity and a good spread of clients between the radios, so we don't have to deal with the increased amount of retransmissions. But even if we do have some retransmissions, then the first attempt will be, the devices will be drawing the contention window number from a pool of in between 0 and 7. Yep. So even if the retransmission happens, the first retransmission will still be very fast, and the second retransmission, pool from 0 to 15, is the equivalent to no retransmissions at all without a QoS enabled So I think that statistically, even if you have the same amount of voice clients that are drawing from a smaller pool initially, you will still see more frames in the air and less sitting on a back timers, like contention window timer.
It's worth noting here that even if you do apply QoS on over Wi-Fi, it's just a statistical advantage. It's not guaranteed. You can apply your voice QoS to your corporate SSID and your best effort or background to your guest SSID, and there's still a chance that a guest user will pull a random number that's lower than the voice SSID, and so it's just a statistical advantage. And also, really, if you are going to be applying QoS on your Wi-Fi, you should make sure that it's also configured throughout the rest of the network, so on your LAN and throughout the rest of the network as well.
Absolutely. Wi-Fi just happens to be the highest chance of being a bottleneck in your network, especially in high contention areas. But statistically, like over time, your voice clients, they will still send way more data than the background traffic or guests that are sitting in lower queues. But a very important thing to understand that this is just a statistical thing. ID. So we have discussed what happens when the device gets access to the medium. We have discussed the contention window timer. So this is the first timer, the first number that all the devices participating in the game wanting to transmit, they draw the number from these initial pools. So what's next? We have said that the devices, they will check the medium if it's free every time they want to send something. So on every IFS timer, every time they want to send something, they will check if the medium is free. And how is this called? What is it? How do they check if the medium is free?
Sure. So it's referred to as CCA. So the physical carrier sense, and there's kind of two parts. Well, actually, I'd say there's probably maybe three parts to it. So we've got the CCA clear channel assessment from the physical carrier sense, and we do something that's called preamble detect and energy detect. And there's also something called the virtual carrier sense, which we'll come to shortly. So what is the physical carrier sense, the CCA? And we have this thing called preamble detect. So preamble detect is if we have, let's say, for example, we've got one access point that's on channel 1, and we've got 2 Wi-Fi clients connected on channel 1 as well. In that area, if our Wi-Fi, one client A can hear client B or the access point at say -80, it's usually around -85 dBm or greater, they're on the same channel, we can do what's called preamble detect. So I can detect that there is another device talking Wi-Fi on the channel that I'm on. If that is happening, I will back off, I will wait, pull my random numbers, do my checks, I can understand what they're saying, and then I will back off, wait for them to finish, and then I will hopefully win my turn and then access the channel. But what happens if there is another type of device that's operating on this channel, but maybe not necessarily a Wi-Fi client device? Maybe it's a non-Wi-Fi device. So let's say we're in 2.4 gigahertz and there's there's a microwave oven, there's some sort of video camera, baby monitor, whatever you want to use that's in 2.4 gigahertz, but it's also, when that's transmitting, that occupies channel 1. So your device now, it's not transmitting Wi-Fi, but it's occupying the same channels that Wi-Fi would occupy. So the device can no longer do preamble detect and I detect that this is another Wi-Fi transmission happening on the channel that I want to transmit Wi-Fi on. I just detect that there's something here called energy detect. So I can detect that there's something happening here, but I don't understand what it is. And the threshold for this is way, way higher. So it's usually at least around 20-25 dBs higher than what preamble detect is. So very important that we understand that if there is non-Wi-Fi in devices transmitting energy on a channel that we want to use and we can't do preamble detect, the back off is a way, way higher, way more sensitive.
Yeah. So that's it. That's the physical part of the CCA, clear channel assessment. So that's the first thing that the devices wanting to transmit data, playing the game, will check before attempting to send anything. Preamble detect.
One good question here.
Sorry?
One good thing here I just want to bring up whilst we're on this subject. One of the first things that we discussed, that what is actually worse in Wi-Fi if you have co-channel interference, when you've got access points or clients all sharing the same channel, or adjacent channel interference where you've got maybe an access point on channel 1 and 2.4 gigahertz, and you've got access point 2 that's on, say, channel 3 on 2.4 gigahertz, and that creates adjacent channel interference. So what would be worse when it comes to CCI or ACI?
So I would say that depends on what we want to answer. But if we have ACI, adjacent channel interference, then the devices, they will not be able to understand their preambles. They will not be able to check against preamble detect. So if you have two Wi-Fi devices, even within the preamble detect threshold, and one device talks, the other device will check. It will see the energy, but it's not high enough because Wi-Fi is not too strong, and it will just talk over it, and this will contribute to collision. So with ACI, these two clients, they will not respect the game. They will just talk one on top of the other, and therefore creating more collisions, slowing everything down even more than when compared to the same two devices sitting on the same channel. That's where they played the game. That's where they hear each other, and they can understand the preamble. Every frame will have a preamble. It's like, the king is coming on. I cleared my throat, so I'm about to talk. So these devices, they understand it now, and they will respect it. They will take a look at the duration ID of their peers, of their associated neighbors, and they will just wait for their turn. And they will decrease the contention window number by 1 every slot time. So that's preamble detect around NEC 85 and energy detect around NEC 62. Preamble detect, Wi-Fi, energy detect, everything. Not necessarily Wi-Fi.
Yep. So just to recap here, in your Wi-Fi network, obviously, when it comes to your access points and your neighboring and rogues, it'd be much better to have no channel interference, but realistically, it's going to happen. Also, there's the chance of adjacent channel interference, and also in 5 gigahertz when you're using wide channels, primary, secondary, OBSS. I know we've mentioned it a few times before, but with a similar sort of thing with adjacent channel interference, you can't do preamble detect if you've got a primary channel that's stepping all over a secondary channel in 5 gigahertz. So in short, we want to have no channel interference if possible, but if we are going to have channel interference, it's better to have co-channel interference than it is to have adjacent channel interference on your Wi-Fi network.
Yeah, or CCI with OBSS on top of it. So overlapping on non-base channels. Yes. That is really bad. Okay, and the second part to the CCA is something called the virtual carrier sense. So we talked about the physical carrier sense, CCA. Now let's talk about virtual carrier sense. We have talked about the duration ID. We know that it's included in the MAC header of every frame that is being sent. We know that all the devices, before they talk, they listen to it. And before, when they sit on the IFS channels, IFS timers, they listen to it. And if they hear anything in the air, they will take a look into the duration ID, not encrypted, and then they will update their virtual carrier sense test. So Matt, how does the virtual carrier sense from the CCA clear channel assessment work?
So yeah, it updates something that's called the nav timer, which is the network allocation vector. And a little bit like the analogy that we said, it's basically is the analogy that we said earlier about when you join a Zoom conference call, when there's multiple people that's attending that Zoom conference, and when you have something that you want to say and you know like how long you're going to be talking for, you can basically announce, hey, Mac, I'm going to be talking about CCA virtual carrier sense for the next 45 seconds. Mac can read that and understand. He hears that. He understands that I'm now going to be talking for the next 45 seconds about the virtual carrier sense. So Mac knows that he basically doesn't even need to continue. He can just go idle and wait for 45 seconds whilst I'm talking about what I am talking about. And then once that 45 seconds is over, we'll continue on through the rest of the game.
Yeah, so that's pretty much it. So CCA virtual carrier sense, well, kicking into duration ID. and we are converting the duration of a frame that someone else is sending to something called a nav timer. Nav timer is set by the duration ID from the MAC header of every frame in the air. Very, very important. Another important thing here to mention that is that even when a station is talking, your Wi-Fi client is transmitting data, the access points on the same channel, they will also have to go through the game, through the contention process before they can send anything, including, let's say, beacons. So sometimes when you do a packet capture in a busy environment, you are expecting to see a beacon being sent around 10 times a second, like every 102.4 milliseconds. But sometimes you will see it being sent like every 105 milliseconds. Sometimes you will see a beacon being skipped. And that's normal because the access point also plays the game identically as everyone else in the Wi-Fi network. Client, access point, does not matter. So that's the CCA, physical carrier sense, and virtual carrier sense. They both are part of a clear channel assessment. That's it, I think, about the CCAs.
Yeah, we say that's it, but that's a lot of stuff that happens each time a Wi-Fi device tries to transmit on the medium. Like that's
for every single frame.
For every single frame, every single device, every single time, all of this happens. When you think about that for a moment, you think, wow, like how does Wi-Fi work, man? And like how does it actually go so fast when there's all of this overhead? So it's quite,
and especially at this very, very low power levels, right? We are talking at 1 billionth of a watt.
Yeah, man.
Energy levels kind of thing. It's crazy.
Yeah.
It's crazy. Okay, so shall we do like a quick recap? I have a logical diagram in front of me, and I will talk you through it extremely quickly. Just to recap, high level, I won't be diving here. What happens in what order when we are playing the game? The game, which is the name of the CSMA CA, which is also called the DCF by a standard distributed coordination function. Mm-hmm. It's all the same things.
I think that would be absolutely lovely, Mac.
Yeah, thank you very much for your approval, Matt. So let's do it then. So we have multiple devices associated to the Wi-Fi network. They are all happily associated. Life is good. And all of them, they want to transmit at the same time. They are all on a voice conversation. They have tons of frames to be sent, and they are contending for the airtime on the same channel. We have a start of the game. First thing, slot time clicks. They want to transmit everything they have in their buffers. Every single device will get the contention window number from a finite pool of initial without cause, 0 to 15. Every single device. Some devices, they will draw 1. Some devices, they will draw 5. Maybe multiple devices will draw 5. And that's fine. They will have a retransmission and collision. But now every device at the beginning, they have contention window number. Another next thing they do is they check if the channel is clear. They go through the CCA, clear channel assessment. If it is not clear, if someone is sending something, if the microwave is up, someone is reheating their burrito, as Eddie would say, they will go back another slot time. They will not change the contention window number. They will not decrease it. They will check again if the channel is clear. And then when the burrito is heated and microwave is off, then clear channel is passed, clear channel assessment. They will want to wait diffs timer. So now all these devices, they don't do anything else. They wait diffs. Then they check if their backup timer, contention window timer, is 0. So it won't be because they've just drawn a number. So maybe you've drawn 0, but unlikely. So let's say that it's not. What's going to happen next? If it is not 0, so contention window number at this slot time is not 0, the devices, all of them, they will decrement the contention window timer by 1. And then they will check if channel is clear again. If the channel is clear, then they will go back to checking if their contention window timer is 0 or not. If it's not clear, then they will have to go back to another slot time, check if channel is clear again, wait diffs again, and then check if their contention window timer is 0. So it happens all the time. And when they are sitting on the IFS timer, so like wait diffs, for example, or before the transmission, they are constantly checking if there is someone else in the air. Microwave, baby camera, another Wi-Fi device, preamble detect, energy detect. And they check if their nav timer set by transmission sent by a different device is 0 or not. So that's the CCA. So let's say that CCA is passed, there is nothing in the air. Some of the devices, like let's say 2 of them at the same time, they have decremented the backup timer contention window. They both hit 0, and they've checked that there is nothing in the air. So what they do, they transmit data. They wait at CIFS, their backup timer is 0, they go. Okay, then they wait short interframe space, CIFS. They wait for an acknowledgement. Since both of them, they send data at the same time, they don't have an acknowledgement. And what happens then? They go all the way back to start, where they draw another contention window number from the first retry pool, which is between 0 and 31. And then they will play the game again. They've selected the backup timer. They check if the medium is clear. If it is, they wait diffs. They check if their contention window number is 0. If it is not, they decrement it by 1 and do it again, like, clear channel assessment, physical, virtual. Virtual is nav timer set by duration ID. If the medium is clear, duration ID, nav timer is 0. They wait diffs, they decrement the backup timer again. And let's say that this time, one device was faster than the other. They have different contention window numbers, and there is no retransmission. It transmits data, it waits, CIFS, it waits for an acknowledgement, it gets the acknowledgement, and if it gets the acknowledgement, then life is good, the transmission is successful. That is it. That covers pretty much all the possibilities that you can have in Wi-Fi. Easy peasy lemon squeezy. I say easy peasy. It took me a while to understand it.
Yeah, of course. It probably takes everyone a little while to get your head around it. I think people probably take for granted how much there actually is that happens in Wi-Fi. I mean, I certainly did before I really started diving in deeper into the analysis side of things. So yeah, it's crazy to see how much actually happens and how Wi-Fi really works.
Yeah, and it's not like regulated by the infrastructure. It's all the clients playing the game, so they have to respect it as part of the standard. They will not be called the Wi-Fi devices like that are capable of doing Wi-Fi from the Wi-Fi Alliance or the IEEE 802.11. They have to respect these rules. There is no other way. Otherwise, they will not get certified. So they will not be allowed to share the medium with us. So that's a little bit funny when compared to, let's say, cellular networks, where everything is scheduled by the infrastructure. It's not in Wi-Fi, okay? And it's fascinating how fast it can go or how slow it can go when you have poorly designed networks that are not fit for purpose. Let's say if you design your office with an omnidirectional IP put every 20 meters in super high density space with no cables in, you will have too many stations trying to actively transmit at the same time. You will have tons of contention. On the other hand, if you put too many omnidirectional access points in the office, so you have an IP every 5 meters, then you will have very excessive CCI, and all these stations associated to the access points on the same channel will be contending for the airtime and playing the game. So if you have 10 APs on the same channel with 10 clients each, you have 100 clients plus these 10 APs, so 110. Every single device will contend for the airtime with every single frame they want to send. So it's also bad. Wi-Fi is a fine balance of multiple things. So you want to give your clients enough capacity without contributing too much to CCI. So if you have great coverage and a secondary coverage and low CCI and enough number of radios versus the number of devices that you expect to see in the network, and when you understand what they're doing in the network, then you can do a good design which caters for these requirements. So we don't have this contention, excessive contention that will slow everyone down because of excessive retransmissions. That's it.
So there you go. Well, hopefully everyone found this podcast very helpful, insightful, useful, and can kind of like picture how Wi-Fi works each time a device wants to access the medium.
Yeah, it's a really, really blasting topic. So Matt, thank you very much for your time today. And guys, thank you very much for watching or listening. If you watch us for some reason, thank you. If you listen to us, thank you. We will see you back in 2 weeks' time.
Yeah, thank you, Max. See you guys in a couple of weeks.
Ciao.